All right, so I was talking about the Coriolis effect. So in the northern hemisphere, currents and objects get deflected so that they spin clockwise um, about wherever they're facing. So as I said before, an example of this is the jet stream, which is an air current in the northern hemisphere, which comes across northern Europe and North America. And so when you think about it, it travels west to east across the globe, which when something's turning is turns like this. So that's like when it turns when something turns clockwise, it's also moving west. Versus in the southern hemisphere, things spin counterclockwise. So the currents down there, they go the other way. So one more thing about air currents is the rain shadow effect, which is, as you can see from this picture, this is India here to the south with the Himalayas in the middle and Tibet in the north. Um, and so the Himalayas block the Himalayas and other mountain ranges block weather that's coming in from the ocean. So the weather, the storms and the precipitation push up against um, the side of the mountain, and so on that side, on the ocean side, there's a lot more precipitation. It gets watered. That's why it's very green down there. Versus on the leeward side of the mountains in the Tibetan Plateau, it's very arid and dry because the the Himalayas block a lot of the moisture. So another thing is the latent heat release and how that ties into air chemistry. So the latent heat release is essentially when you've got a a thunderstorm, for example, and it's moving along the surface of the Earth, and it's sucking up heat into it because there's a lot of hot air on the surface of the Earth, and so the thunderstorms are cool, so that it sucks the air up into it, and then it funnels it up in a convection current within the storm itself, and cools the air, makes it more dense, where whereby then the storm reaches its saturation point and dumps the water back onto the earth in the form of rain, where then it is warmed and sucked back up into the storm, and the cycle is repeated. So the air chemistry behind this is the less dense air is at the top of the is at the bottom of the storm. Excuse me, and it gets sucked up, becomes more dense, and falls as cool rain. So the final thing are ocean currents. Um, so we'll be looking at patterns of surface and deep water circulation and the causes and effects of El Nino and the Southern Oscillation. So just a couple of important ocean currents are the Gulf Stream, which runs on the eastern side of the U.S. out towards Europe, which gives Europe milder climate, even though it's much farther north than most of the U.S. is. It still is almost as if you lived in, say, Kansas. Um, then there's the Southern Ocean currents, which run unimpeded across the Southern Oceans, which makes down here by Cape Horn and just kind of the rest of the Southern Ocean, just north of Antarctica, very stormy because you've got very fast turns circling the globe without stopping it ever. Then there's also the trade currents, which help ships go across the ocean. So, for example, this one here going across the Pacific to places like Singapore down here, Indonesia, and Africa. Also from Africa up to here in North America is very helpful. They're created mainly in part by wind, water density, salinity, and gravity. And we'll look more into that in a little bit. So an important thing is the thermohaline circulation, which is a cycle of deep water ocean circulation. The name thermohaline, thermo meaning temperature, haline meaning salt, which which essentially means how hot or cold and how salinated certain parts of the water are. So when you have water circulate, it comes up through the Gulf of Mexico, which is very warm, up through the Gulf Stream, again, warm climate, warm water, warm current. It comes up into the Arctic Ocean up here near Greenland and Svalbard over here, and where it releases heat into the air and sinks down and becomes very salty and thus travels the length of Greenland down to northern Canada down here under the Gulf Stream actually, which is kind of cool. You've got one current going up, one current coming down, so I thought that was pretty cool. And then down up into here where it comes around and then warms back up over here. So really, there's a lot of heat release up in the northern parts of the ocean, which is kind of interesting because the northern parts of the ocean are really cold. So I like this picture. So the gyres are big. It's a system of ocean currents, which just slowly spin either clockwise or counterclockwise depending on the hemisphere and the Coriolis effect. So again, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere, and so they kind of spin slowly and create like a small whirlpool. Not you're not going to get sucked down in the middle of it and die. Although you can die in the ocean, that has happened before. But they spin slow enough, and then they kind of collect things in the middle of them. An example of that, as you can see from the picture, is the Great Pacific Garbage Patch, which is just a big patch of garbage of all the garbage that was in the northern Pacific Ocean that got caught by the northern Pacific Gyre and has just slowly spun into a big mound of garbage, which some people say is the size of Texas. Not sure if you can visualize that, but it's pretty big. So gyres are a pretty important thing in ocean climates. Another important thing is upwelling, which is the recirculation of deep cold water back to the surface, which so you've got a lot of cold water down below, and then in the areas of upwelling, which are right next to coastal California and Baja California down here, off the coast of Peru and Ecuador and South America, east kind of Namibia, Angola, Namib Desert down over here, East Africa, right over here, and then off the coast of Australia. Those are the main areas of upwelling. As you can see, this is a map of ocean productivity. So those areas I just highlighted are very productive. That's because upwelling stirs up a lot of nutrients from the bottom of the ocean and feeds them back up to the surface where the phytoplankton can feed off of them, and so then they grow in numbers, and then other fish can come in and they eat the phytoplankton, and their populations grow as well. And then we humans come in and catch all of them and destroy our ecosystem. So I think this is the final thing. The final thing that I'm going to talk about is El Nino, the El Nino Southern Oscillation. There are phases of warm and cool air coming across the equator in the Pacific Ocean. This globe in the background is an infrared camera photo, and so the white, if you can see down here, means that it's very warm and lots of rain. So versus over here, it's pretty blue and not very warm and not very rainy. So El Nino years, we just had one last year actually. That's part of the reason why we didn't get a lot of snow. It's a particularly strong El Nino year. There's a lot of precipitation that comes off of the Pacific Ocean over in this area over here by the equator off the coast of South America, which means that you've got a lot of rain coming in into the southwestern United States, Mexico, Central America, versus it's cooler and drier over in the northeastern United States, where obviously we are. And so La Nina